Okay, so for question 2, we are given compound W has the molecular formula C7H7OCl. So again, we'll attempt to calculate the degree of unsaturation. Yeah, so if you remember what we mentioned earlier on, for atoms such as halides, in the calculation of degree of unsaturation, we will treat them as hydrogen. Yeah, so therefore the maximum number of hydrogen that a 7 carbon unit can have, assuming that it's an alkene, will be 2n plus 2, so that will be 16. Okay, minus of 8 hydrogen, yeah, divide by 2, so in this case the degree of unsaturation will be 4. Yeah, so 4 degree of unsaturation, given that it's a relatively simple elucidation kind of question, right, you might suspect that a phenyl ring might be present. So a phenyl ring might be present. Yeah, some of you like to call it as benzene ring. I think that is still okay colloquially, but benzene ring, strictly speaking, is referring to C6H6. Yep. So if you have an arene where it is obviously a C6 kind of arene, then I think the best term to use is phenol. But some of you might be confused with the word phenol, which is a functional group with the OH bonded to the phenyl ring. Yeah, so if you want to avoid conclusion, then maybe no. Okay, but in this case, I think it's quite clear cut because question says it's an aromatic compound. Yeah, since it's an aromatic compound, I think it agrees with the clue that it's a phenyl ring. Yeah, so from here, therefore, that you don't expect it to have any CC double bond or any other degree of unsaturation. Yeah, even aldehydes or ketones, no. Okay, of course, there's another clue being given to us explicitly. It contains 2 functional groups. Okay, usually for phenyl ring or benzene or arenes, we don't consider that as a functional group, although strictly speaking, they are lah. Yeah, so in this case, we might want to look beyond a phenyl ring or benzene ring as functional group. Yeah, so we will need to look at the reactions given to us, and we see how we can proceed from there. Okay, so the first thing is reaction number 1. Aqueous silver nitrate is added, warm, we get a white solid. Yeah, so in this case, I expect the white solid to be silver chloride. Yeah, it is quite obvious from here because number 1, white solid is formed, and then after that is soluble in excess ammonia aqueous. So if you take a look at the second last page of a data booklets, yeah, that is an indication of the precipitate silver chloride. Okay, then the second clue is also quite common for everyone. Aqueous bromine in excess, you get a white solid with the molecular formula 379.2. Yep, so clearly the molecular formula jumps from a relatively small number to a relatively huge number. Yeah, so if you just want to do a quick calculation, we can calculate the molecular formula for, or rather the relative molecular mass of C7H7OCl, or meaning W. So we can do that by taking 12 multiplied by 7, so the MR. Okay, 12 multiplied by 7 plus 7 plus 16 plus 35.5. Yeah, so if we simply just take a calculator and calculate 12 times 7, that's 84, plus 7, that's 91, plus 16 plus 35.5, we'll get 142.5. Okay, so over here we'll get 142.5. You notice that it jumps from 142.5 to 379.2. So I would expect some form of substitution or addition to take place. Yeah, but since we know that there is no CC double bond, then it's definitely not an addition reaction, so it's likely to be some form of substitution reaction. Okay, and since we know that there's a phenyl ring, and this particular compound W contains oxygen as well, so perhaps we can guess that maybe a phenol might be present. Okay, so a phenol functional group might be present. Yeah, so that's what we can tell from reaction 2. Okay, and some of you might not be aware that we can actually tell how many Br has been added solely by looking at the relative molecular mass. Okay, how do we know? I'm going to show the working here. Yeah, because you know that my unknown W contains 1 Cl. So if you if it contains 1 Cl, that means that the relative molecular mass must end with a decimal place 0.5. Okay, and my final relative molecular mass ends with 0.2. Yeah, and if you look at the data booklets, the relative atomic mass of bromine is 79.9. Okay, so that will be 0.9. Okay, so in order to find out how many bromine is being added, we just add 0.9 until we reach 0.2. Okay, so if 1 bromine is added, then the ending will be 0.4. If 2 bromine is added, that will be 0.3. If 3 bromine is added, then we'll end with something 0.2. Yeah, so from here we can tell that 3Br substitutes, okay, for 3H. How do we know it must be substitution? Well, I think earlier on we emphasized that it should be electrophilic substitution because all the clue point towards having a phenol functional group. Okay, yep, and then moving on to reaction 3, we are given alkaline KMnO4, heat under reflux and then acidify, and then you notice that your MnO4 minus decolorize, one organic compound is formed with relative molecular mass of 138. Yeah, so since it goes from like something 0.5 to like a whole number, you can sort of guess that maybe the chlorine is gone, and when you guess that the chlorine is gone, you could also guess that the chlorine is perhaps part of your alkyl side chain, which undergoes side chain oxidation. Yeah, so with that, I think reaction 1, 2, and 3 combined, we will have a bit of an idea about what our unknown or the structure of our unknown. Yeah. And if you take a look at reaction 4, it's just a very simple reaction. You add sodium and then colorless gas evolve, white solid form, which is soluble in H2O. Yeah, so you would expect this to be a simple acid metal reaction. Yeah, so essentially it's a redox. So in this case, your colorless gas is hydrogen gas. Yeah, so it's actually a single electron transfer reaction where sodium transfer an electrons to the phenolic OH functional group, and eventually you get an O minus Na plus. Okay, and then of course hydrogen gas is involved because 2 hydrogen radical from the homolytic cleavage of the OH single bond will give us a hydrogen gas, or 1 mole of hydrogen gas from 2 moles of hydrogen radicals. Yeah, so these are some of the ideas you can have at this stage. You notice that I didn't even start doing the question. Okay, I can just analyze the reaction, have an idea about what's going on before we go straight and work on the problems. Okay, then finally reaction 5, we added sodium hydroxide, room temperature, we get a color solution. Yeah, so solution reaction 5 basically tell us that indeed a phenol functional group might be present. Yeah, because phenol is the only kind of alcohols which we learned which can dissolve in sodium hydroxide. Yeah, the other alcohols are not acidic enough to react with sodium hydroxide. Okay, so with all the clue, I think we can easily answer the questions which follows. Okay, so first let's take a look at question A1. What is a solid form in reaction 1? So we can go back here and take a look. Okay, so earlier on we confirm it to be silver chloride. Okay, name the functional group in reaction 1 shows to be present in W. Okay, so what is likely to be present in W in reaction 1? Yeah, so I think earlier on we have sort of tried to sketch out a picture of our unknown. Okay, but we didn't quite draw it out, so we can attempt to draw it over here. Yeah, okay, so we know that I think number 1, right, my phenol ring, the question to ask yourself is it likely to be mono, okay, di, or tri-substituted? Okay, so this is one question to ask yourself. Yeah, so mono substituted is impossible. Why? Because mono substituted can only be a phenol, which is a OH directly bonded to a benzene ring. But you know that it must contain another functional group bonded either at the 2nd, 3rd, or 4th position. The reason being, if not, I won't be able to have side chain oxidation, or reaction 1 would not even occur. Yeah, so the question is, Is it likely to be di or tri? Yeah, so of course, if you think of it as di substituted, then one of my substitute, one of the position will be CH2Cl. Yeah, you can easily take a difference between the formula, and you will notice that the remain is a CH2Cl. Yeah, then if not, could it be tri-substituted? If it's tri-substituted, right, then my unknown will be CH3 and then a Cl here. Yeah. However, if this is the case, right, then you would be aware that this particular CCl bond, being sp2CCl, will not be able to undergo nucleophilic substitution via reaction 1. Yeah, because of the partial double bond character. Yeah, so therefore from here I can predict that tri-substitution is impossible. Yeah, so this particular structure is not likely to be the one. And of course this structure could be, okay, but we are just not sure at this stage the substitution pattern. Of course we can be sure by further looking at the clue given here, but at this stage we don't have to move in that particular direction. Okay, yeah, then I can therefore conclude is di substitution, and my side chain is therefore some form of chloroalkane. Yeah, so if I need to name the function group that I can deduce from reaction 1, that will be chloroalkane. Okay, and then for part 3, based on reaction 4, suggest the possible function groups that could be present in W. Okay, so I can only base this on reaction 4, which is the reaction between sodium and the OH group. Yeah, so from here I can conclude alcohols, okay, or phenol. Okay, and then for part 4, which of the functional groups you have named in part 3 is confirmed in reaction 5? Explain your answer. Okay, so from here I think it is quite obvious that we are looking at phenol here, because only phenol can undergo acid-base neutralization reaction with sodium hydroxide. Yeah, so that is the very basic conclusion we can have. Why is that the case? Because phenol is acidic enough to react with sodium hydroxide. Yeah. Why is that the case? Because the phenoxide anion allows the negative charge to be delocalized into the phenol ring. Yeah, which helps in charge dispersal. Okay, so therefore here we are saying that phenoxide anion is more stable as compared to alkoxide. Okay, because for alkoxide anion, the negative charge at the oxygen is being enhanced by the electron donating alkyl groups. Yep. Then from here, moving on to part B, we are supposed to deduce the molecular formula of the organic products formed in reaction 3. Remember here the keyword is molecular formula, so you're not supposed to draw any structure. Okay, so we are simply focusing on molecular formula here, which can be concluded from which is formed in reaction 3. Okay, so for reaction 3, we can be sure that side chain oxidation takes place. Okay, now first of all, right, we need to understand the what our molecular formula of W is. Okay, so for the molecular formula of W, we need to go to the front. It's C7H7OCl. Okay, so it's C7H7OCl. Yeah, and earlier on, remember we have sort of concluded that the side chain must be CH2Cl, right? Okay, so therefore, when side chain oxidation occurs, I should subtract off CH2Cl. Okay, I don't mean that the whole group is gone. I just mean that I think it's easier for us to just subtract it off first, and then maybe to add something later on. So after we subtract off, we will have C6H5O. And remember, for side chain oxidation, the side chain becomes carboxylic acid. So we need to add CHO2. So eventually we'll get molecular formula C7H6O3. Yeah, so this will be the answer to part B. Yep. Okay, then moving on to C part 1, deduce the molecular formula of the white solid formed in reaction 2. Again, we are going to use the same logic. So the molecular formula for W is C7H7OCl, H7OCl. Okay, what we're going to do is, because we understand that it's a tri-substitution, so we need to minus off 3 H's, and then we need to add 3 bromines. Okay, and that's it. I'm going to get C7H4OCl Br3. So this can be done quite easily. Then what type of reaction takes place in reaction 2? I think earlier on we have highlighted to you. It should be electrophilic substitution. Okay, substitution. So I think we have already concluded that when we were trying to solve for reaction 2. Remember what we did earlier on? We concluded that it cannot be an addition, it has to be a substitution, and obviously it involves an electrophile. Okay, then part 3, explain how the formation of this compound show that compound W is an aromatic compound rather than an aliphatic compound. Okay, I think first of all, right, if W is not an aromatic compound, it will have undergone addition reaction. Okay, so if it undergoes an addition reaction, then this particular step where I subtract off 3 H's becomes redundant. Okay, you guys get it? So it becomes redundant. But the fact that the 3H are being substituted rather than it being retained, right, shows that it is indeed a substitution reaction, which means electrophilic substitution took place. And for electrophilic substitution to have taken place, I must have a benzene ring, and in this case I do not need a Lewis acid because the phenolic OH allows the lone pairs of electrons to be partially delocalized into the phenol ring, which enhance its electron density, allowing it to undergo electrophilic substitution much more easily. Therefore, I do not need the Lewis acid to generate the electrophile. So if it's an aliphatic compound, meaning just with a CC double bond, then I would not expect electrophilic, or rather I would not expect substitution to have taken place. I would have expected addition reaction to have taken place. And for addition reaction, in this case, it has a degree of unsaturation of 4, which we determined earlier on. That will mean that on the average, I probably will be adding 4 Br and maybe 4 OH across the double bond. But of course, that is not that is not for sure. Because it could be a mixture of a different, maybe one of the double bond is adding 2 Br, the other double bond is just 1 Br and 1 OH. But in this case, it's quite clear cut because I'm only getting one compound, which clearly 3 of the Br substitutes 3 of the H. So therefore, the reaction is, compound W is expected to be aromatic rather than aliphatic. Then name the functional group present in W that is confirmed by reaction 2. I think earlier on we talked about it. For us to have tri-substitution without the need to have a Lewis acid catalyst, that means it must be sufficiently activated enough. So therefore, I'm looking at phenol. Okay, then what other reaction confirms that W is aromatic? Explain your answer. So the other reaction which confirms that it's aromatic is actually reaction 3, because for reaction 3 it is obvious that it undergoes side chain oxidation. Side chain oxidation, or oxidation of long alkyl chain within the boundary of your syllabus. Of course, you only know that you learn that only in only when the side chain is bonded to the benzene ring. So with that, then side chain oxidation is likely to have taken place at the side chain bonded directly to the benzene ring for our case here. So with that clue, I can therefore conclude that, or I can therefore confirm that W is aromatic instead of aliphatic. So in this case, it will be reaction 3, and then the reason being side chain oxidation occurs. Okay, so for part D, you have now enough information to deduce the structure formula of W. Okay, so I need to show the displayed formula. Yeah, then earlier on, I think we can safely say that whatever I drew here deliberately is not correct, because I'm drawing the 1,2 disubstituted uh, benzene or phenyl aryl system. Yeah, but if it's 1,2 disubstituted, knowing that OH is 2,4,6 directing, right, my BR will only be able to add to this position and this position. Yeah, so to check out or to confirm or to deduce the actual substitution pattern, I need to make sure that 2,4,6 is free from any substituents. Yeah, so because of that, my substitution pattern should therefore be only 1,3. Okay, so with that, then the displayed formula for W, it should be simply an OH and then with a benzene ring. Okay, and then the third position has a CH2Cl like this. Yeah, based on your syllabus requirement, remember that benzene ring no need to have displayed formula. Yeah, because you are allowed to show represent it with a hexagon with a circle inside. Yeah, so displayed formula only apply to things beyond that. Okay, so do remember this and not waste time writing out display formula for everything. And then finally, for D parts 2, explain clearly why you have placed each of the two functional group in their particular position. Yep, I think we have explained quite a bit about this earlier on. So I think first of all, the phenolic OH directs the incoming nucleophile to the 2, 4, and 6 position. Yeah, so therefore, the substitution pattern for W must be 1, 3 in order for the BR to be able to add to the 2, 4, 6 position. Okay, so therefore my phenolic OH being ring activating must be directly bonded to the benzene ring, of course. And then why is it an aliphatic chloroalkane rather than a chloroarine? I think we have also explained that earlier on. Because if Cl is bonded directly to the benzene ring, then number one, we will not be able to get a positive test for reaction 1. Yeah. So if Cl is directly bonded to the benzene ring, reaction 1 will not give us a positive test because the CCl bond has partial double bond character, and breaking of the CCl bond under the condition described in reaction 1 is not possible. And in addition to that, for reaction 3, you notice that the MR of the final product does not have a 0.5, so therefore that means that the Cl is gone when reaction 3 takes place. Yeah. For Cl to be gone, the Cl must be part of the LQ side chain, which undergoes side chain oxidation. Yeah, if Cl is directly bonded to the benzene ring, side chain oxidation will not cause any oxidation of Cl, at least within the boundary of your curriculum. Yeah, then with that, we will therefore be able to conclude that the Cl must be bonded to the sp3 carbon rather than the sp2 carbon, which is part of the benzene ring. Yeah, so with that, I think with the reasonings I have given, then I would be able to successfully defend my answer to part 1, where number 1, the 1,3 disubstituted pattern, and number 2, why chlorine must be bonded to the side chain rather than directly to the benzene ring.